Yeah, so hi everyone, good afternoon, depending where you are in the world. Um, yeah, so it's my great pleasure to introduce Professor Matthias Caro, who today will be giving us a talk on recent paper. So this PRX, you can see it on this slide. So the title of the talk is Learning Quantum States and Unitaries of Bounded Gate Complexity. So let me just start by first thanking Professor Caro for agreeing to give this seminar. And so we're hoping this will serve as a way of kind of establishing kind of contact between our two groups here at Stellenbosch and Warwick. So I know that we have people here who are also interested in quantum machine learning. So before I hand over to Professor Caro, let me just maybe give let me read out his bio. So Matthias is currently an assistant professor at the Department of Computer Science at the University of Warwick in the UK. His research lies at the intersection of quantum computing and quantum learning theory, contributing to rigorous understanding of the potential limitations of quantum machine learning. So before joining Warwick, he was a postdoc researcher at the Free University in Berlin and a postdoctoral visiting research fellow at the California Institute of Technology. So funded by a fellowship of the German Academic Exchange Service. He completed his PhD, which was recognized with multiple awards under the supervision of Michael M. Wolf at the Technical University of Munich, where he mainly worked on statistical properties of variational quantum machine learning models. So yeah, let me thank you again for offering to speak. And yeah, let me hand over to you now. Thanks.
Well, thank you very much. Thanks a lot for inviting me and giving me the opportunity to present here. As you heard, my name is Matthias. I'm based at the University of Warwick, and I'll be telling you about this recent work on learning quantum states and unitaries of bounded gate complexity, which I actually did before joining Warwick. And this is work that I did together with Haimeng, Laura, Ishan, Ihui, and Robert. And really, Haimeng, Laura, and Ishan deserve a lot of the credit for this work. They were the students who did most of the heavy lifting here. So my plan is, I would say, a somewhat ambitious one in terms of what I want to cover, but I'd rather not get through all my slides and have you follow me as far as I go along. So if there are questions along the way, please feel free to interrupt me and just ask. All right, so before I start with any technical detail, I first want to tell you what you're going to hear about. So the motivation that I've decided to give you is a classical motivation. So in classical probability theory and classical computer science, there is in a sense, very basic and fundamental problem. So you should imagine that there's some unknown probability distribution P over some, say, finite alphabet. And what you get are IID samples xi drawn from this distribution. And now your task is to take these samples, process them, and to output an estimate for the probability distribution. So more precisely, you should output an estimate that is epsilon close in, say, 1 norm, which up to a constant factor is the same as total variation distance. And there is there's good and bad news about this. The good news is we know the sample complexity precisely. So we have upper and lower bounds, and they're tight. And the sample complexity scales like the size of the support of the distribution. This is what I called capital X here, divided by epsilon squared. The bad news is that the scaling may or may not be good for you, depending on how large your support is. So given this classical problem, there's a natural quantum counterpart, and presumably most of you will be familiar with this counterpart. It's called quantum state tomography. So in quantum state tomography, you have access to copies of an unknown quantum state rho, and your task is to perform a measurement on these copies, process the measurement outcomes, and then produce an estimate for the state that is close to the true state. And here the natural distance measure would be the trace norm. I decided for 1 norm, so there's like just a factor 1/2 missing. And similarly to the classical case, this is a hard problem. So in particular, if you try to do this for an n-qubit state, we know that the sample complexity, so the number of copies of the state that you need, scales like 2 to the 2n over epsilon squared. So in particular, it scales exponentially in the number of qubits. So this is mostly bad news because it means that quantum state tomography is not feasible even for medium-sized quantum systems, at least not in the way that I phrased it here with respect to the one norm. And now if you care not about a quantum state that's fixed in time, but you care about learning a quantum process, so the evolution of a quantum system, things obviously don't get better. So here you imagine you have access to copies of a quantum channel, which you should think about as black boxes where you can produce you can give an input and it produces an output for you according to the channel. And the most general kind of quantum experiment you could do here is to input an entangled state. So sorry, to input half of an entangled state into the quantum channel. And then you would have like this interleaving processing where you apply a channel, then you apply a control operation, you apply the channel again, and so on. And in the end, you measure, and your goal is to produce, after processing the measurement outcomes, an estimate of the channel. And here you can again argue which norms to pick. I chose the diamond norm for this demonstration. And here something messed up my slide. Here there is a folklore result that you can do it with a number of copies that scales exponentially, but actually we know that this is necessary. And in the unitary case, we have a tight characterization, which was recently achieved by Jungwon Ha and co-authors. So also here we have an exponential scaling and we don't know how to overcome it. And in fact, we cannot overcome it. So this raises the question of, can we do better quantum tomography in some scenarios? In particular, can we do quantum tomography in a way that's feasible? So there's, in fact, a whole suite of assumptions that are known to allow for better tomography. One of the earliest ones is to assume that the state is not just an arbitrary quantum state, but it's a stabilizer state. Or in the case of the process, assume that it's not an arbitrary unitary, but it's a a unitary implemented by a Clifford circuit. And in those cases, we know efficient learning algorithms. This has been extended recently to the case where you consider Clifford circuits that have at most logarithmically many T-gates in them. And here, the reason why I focus on logarithmically many is because if you go beyond that, the sample complexity will blow up. And on a different, in a different vein, there are efficient learning algorithms based on MPS representations or for states prepared by shallow quantum circuits. And likely there's lots more that I'm not covering on this slide. So this means that while general quantum tomography is infeasible, if you make additional assumptions, it can become feasible. So this raises the questions of what are good assumptions to make. And for the purposes of this talk, we'll have one guiding question, which is that I think about states and processes that you encounter in nature as objects of polynomial complexity. So this is, I would say, the computer science perspective, where if the state exists, it has to have been prepared in some reasonable time. So in particular, it should have been prepared by a polynomial size circuit. And then you can ask, is this assumption of polynomial complexity already an assumption that allows for learning? So can we efficiently learn states or unitaries if I promise you that the gate complexity is bounded? And then how efficiently can you do it? So I should put out the disclaimer here that we're not the first to ask this question. So in particular, this question has been asked and partly answered in some prior works that effectively showed that if you assume a polynomial complexity, you can get better than these exponential and n scaling sample complexity bounds. But the bounds weren't tight, and also there was no study of computational complexity. So the contribution of this work is to produce tight bounds on learning states and unitaries of a bounded complexity, and to also give some insights into the computational complexity. All right, so that's what I want to talk about today. Any questions about the high-level motivation and the rough task that we're going to look at. Okay, it doesn't seem to be the case. Then I'll continue onward. So I did my motivation. So I'll now tell you about the first part of the results of this work, which is learning quantum states. Then we'll talk about learning unitaries, and then presumably I won't have time to talk about quantum null free lunch theorems, but that's okay. So in this part of the talk, we're going to ask and answer the question of how easy or hard it is to do tomography for bounded complexity states. What you should think of here is the following experimental setup. So you have a quantum state psi, and for the purposes of this talk, I'll only consider pure quantum states. And you assume that this quantum state psi is prepared by applying a quantum circuit that has G many gates to some fixed reference state. What reference state that is doesn't really matter, so just assume it to be the all zero state. It just has to be a known reference state. Okay, and then you assume that you're given n copies of the state psi. So in particular, I'm not telling you what the circuit is. I'm just giving you copies of the state and promising you that there is such a circuit. And your task is to produce a description of a hypothesis psi hat that hopefully is a good approximation to the true state. Okay, so it's the same as the state tomography question from before, only with this additional promise that the state comes from a circuit with G many gates. And when I say this, you should think a quantum circuit that is two local. So every gate can act on two qubits at the same time. It doesn't have to be geometrically local, so it's fine if the two qubits are actually far apart. But for simplicity, we focus on two-qubit gates. You can, in principle, extend our analysis to any constant k. So if you act on k qubits at the same time, it's just easier to do for two. Okay, so the first question to ask is, what is the sample complexity here? And what we show is that the sample complexity scales like the number of gates over the desired accuracy squared. Okay, so if you give me roughly g over epsilon squared many copies of an unknown state psi that's promised to come from a g-gate unitary, this number of copies is necessary and sufficient to get an epsilon accurate trace norm approximation psi hat with some constant success probability. Here I pick 2/3. And this success probability you can increase by standard tools. So for the purposes of this talk, let's always take the constant. All right. A few words about this result. So first, you see that I wrote this theta tilde. So here the tilde hides logarithmic dependencies in leading order terms. So it hides a log g over epsilon. But it does not hide any system size dependence. So from this perspective, I'm not cheating. The number of copies that is necessary and sufficient has no explicit system size dependence. Of course, if your number of gates depends on the system size, that gives you some system size dependence, but there's no explicit dependence on system size. And then another nice feature about this theorem is to achieve this upper bound, we use a procedure that only measures single copies of the state at a time. I highlight this because in general mixed state tomography, you actually, at least for achieving the optimal bounds that we know, and to some degree we also know that this is needed, you need to perform a measurement simultaneously on many copies of the state at the same time. So this is, well, I would say technologically quite challenging. It requires you to have a big quantum memory. This is not required in the pure state case. This was known before, but I'd argue that we simplify this a little bit. Okay, and then finally, as I said, you can increase the success probability and there's a tight dependence there. I'm just not showing it for simplicity. Okay. Now, I want to shortly tell you how we prove this, because I think the method is intuitive and therefore hopefully I can explain it in one slide or two. And I'll first tell you about the upper bound. I'll make a somewhat weird assumption, which I'll explain later. So let's assume that the number of gates is not too small. in particular, let's assume that the number of gates is at least half of the number of qubits that we have. I'll tell you why this is relevant in a bit. Our proof comes with a few ingredients. So the first ingredient is a tool set called covering numbers. Here for the class of states that can be prepared by circuits with G gates. This is something we take from prior work. And what you should think about covering numbers as saying is you have your huge, potentially huge state space. And now what you'd like to do is you would like to discretize your space. So you want to identify some representative states such that no matter what state you care about, one of your representative states will be epsilon close to it. So in that sense, you're discretizing your space. You can also think about it as covering the space with balls of radius epsilon. And in many cases, this is a more accurate measure of the size of an object than its ambient dimension, right? Because we're looking at n qubit states, so the ambient dimension still is exponential in n. The point is that these covering numbers scale much better. So what you see here is that the logarithm of the covering number of the set of states that can be prepared by G many gates, this logarithm scales essentially linearly in G and logarithmically in n and 1 over epsilon. So this means that the effective dimension of this object is not linear in n. It's in fact more linear in G. And sorry, it's not linear in 2 to the n, I should have said, but linear in G. Okay, so this is the first ingredient. And now the intuition is that you have a control over how many representative candidates there are, right? So you've discretized your space. Now you want to find out which of the points in your discretization is the best approximation to your unknown state. To do this, we use another tool from prior work called quantum hypothesis selection. This was introduced by Badeshko and Adorno. And here, they do it in a more general context, but what it means for us is you can find the closest state in one of these covering nets by estimating a number of expectation values that scales only quadratically in the size of the covering net. Essentially, you compare the pairs of points from the nets. And well, for these, you want to estimate essentially trace distance between them. So it makes intuitive sense that Holevo-Hellström measurements should play a role here. The procedure that Badeshko and O'Donnell use for this is actually quite involved. We simplify this a little bit by noticing that since we focus on the pure state case, our measurements have constant rank. So these Holevo-Hellström measurements for for a pair of pure states is always rank 2. So we can just use single copy classical shadows with random Cliffords to estimate these expectation values very efficiently. And in particular, we can estimate these with a sample complexity that scales logarithmically in the number of expectation values we care about. Okay, and the number of expectation values we care about is the square of the size of the covering net. So you take a logarithm of that. That means that the thing that matters is the logarithm of the size of the covering net. And above, we argued that the scale is essentially linearly in G. So this shows how you get this scaling that I claimed for the sample complexity upper bound. Now, why did I have to make this assumption about G being at least n-half? So the reasoning that I gave you gives the following upper bound. So it's a G log G over epsilon plus G log n over epsilon squared. Now, if G is too small compared to n, then actually the log n might be a problem because it might be that the log n actually scales more quickly than the log G. So I cannot absorb it here anymore. So it's a little bit of a technical concern. But essentially, if G is less than n-half, there are going to be qubits that are never acted on, right? Remember that I said that a gate acts on 2 qubits at most. So if you have less than n-half gates, some qubits will not be acted on. So the idea is now to first figure out which are the qubits that are actually acted on, and then run the procedure from before. So here, you don't have to understand the algorithm. The point of the algorithm is it's a simple one. So there's a simple way of identifying the qubits that are acted on non-trivially, and then you can run the procedure from before. Okay. Questions about the upper bound, because if not, I would continue with ideas for the lower bound. Okay. Okay, then let me tell you about the lower bound. So for the lower bound, we do something that seems weird at first glance. So we start out by taking all of our gates and squishing them into the first logarithmically in G many qubits. So what I mean by this is we start from a circuit that looks like this, like, I don't know, something like this, potentially a brickwork circuit. And then I just say, okay, let's now not have any gates on the last few qubits. Let's just have gates on a very, very small number of qubits in the beginning. This is arguably not the most interesting way of using the G many gates that you have, right? It severely limits which kind of states you can reach because you're just going to get the zero state on the remaining qubits. But from a proof perspective, it's nice for the following reason. So we squished all of these gates into the first logarithmically in G many qubits. Now, it's kind of a folklore result, and I think you can find it in QSUN Chuang, maybe, that if you have, let's say, k many qubits, on the order of 2 to the k many unitary gates suffice to implement arbitrary k qubit states. Okay, so what we did is essentially we said, set k to be constant times log g with a suitable constant. Then we have a number of gates that's exponential in our number of qubits, so we can implement all states on those qubits. Okay, so if you look at this picture again, what we're doing is we're rewriting the circuit so that on the first few qubits, we can get arbitrary states. And on the last qubits, we just have the all zero state and we don't care about it. So the reason why it's useful to create all states on those qubits is because then we can use existing machinery for proving learning lower bounds for states. For those who are interested, you do this by constructing a packing net that has a large size, but that at the same time, so the large size means that you get a lower bound on the number of bits required to epsilon approximate. Oh, sorry, this should read state, not channel, the unknown state. But at the same time, you can construct this net in such a way that the accessible information from a single copy of the state is limited by the Holevo information of the ensemble, and the Holevo information is small. So this is not our idea. This is the same technique that Zhongwan Ha and co-authors used. And now if you use this, you get a total number of copies that's at least g over epsilon squared up to this log factor. Okay. So this already concludes my proof of the first theorem. So I've argued that no matter what circuit you look at, we can learn this by a covering number arguments from a number of copies that scales roughly linearly in G. And even if you focus only on those weird states where all of the gates are on a few qubits only, we can get lower bounds that match that. Okay. Any questions about this sample complexity result? Okay, then the next point of business is to talk about computational complexity. So here, the basic idea is that what we managed to do is we came from general tomography where even the sample complexity was exponential, right? So if you need exponentially many copies, there's no way you can do it computationally efficiently. Because in computationally efficiently, you cannot even measure all of the copies, right? So what we did is we reduced the sample complexity to something that scales efficiently in the number of gates, but it's still not clear whether you can do it computationally efficiently. In particular, the algorithm that I showed you before is extremely inefficient because it relies on covering net arguments. So you have to construct a covering net, which is typically very inefficient. And then even though we're using this hypothesis selection algorithm, it's still effectively a brute force comparison of all elements in the covering net. And that's just too big to be efficient. So this raises the question of whether you can do it computationally efficiently. And in some sense, the answer is just no. So what we show is that under a certain cryptographic assumption, solving this learning problem, so learning an approximation to an unknown state that's promised to be prepared by a circuit with linearly in G many gates, this just requires a time that scales exponentially in, well, the minimum of G and the number of qubits, but you can think of this as essentially scaling exponentially. And the assumption that we make here, I'm not going to say much about it. So the assumption is that a problem called ring learning with errors cannot be solved by a quantum computer in sub-exponential time. The only thing I want to say about it is that learning with errors is a problem that's commonly considered hard for quantum computers. In particular, post-quantum crypto systems are based on this assumption. So the assumption itself is not that ridiculous. People might disagree with us about the sub-exponential part. I think the more standard phrasing of the assumption is you cannot do it on a quantum computer in polynomial time. Then we still get a computational complexity lower bound. It's just a weaker one. Okay, so this means under this assumption, which is reasonably widely held, is my impression, we don't expect to be able to do this efficiently as soon as the number of gates is super logarithmic. And in particular, one thing that's nice about our proof is that actually the proof only uses circuits that have Clifford gates and super logarithmically many T gates. So not just is this true for general circuits with super logarithmic size, it's really true for Clifford gates with super logarithmically many T gates. So this answers a question that Srinivasan Arunachalam and Anurag Anshu raised a few years ago. And it shows that for learning beyond Cliffords, there is really a relatively sharp transition around logarithmically many T gates. If it's at most logarithmic, you can do it. But if you go even slightly beyond super logarithmic, it's not possible anymore. And the other thing that you will notice about this lower bound is that in the regime where G scales logarithmically in N, the lower bound just gives a polynomial lower bound, right? And in fact, in this regime, you can do it efficiently. So in this regime, we give an efficient learning algorithm. It's not a particularly complicated one. Essentially, you again first have to identify which are the logarithmically many qubits that are acted on non-trivially. And once you know that, you just do full tomography, which now is efficient because you're dealing with a logarithmic size system, right? And the final comment is, as I said, so if we only require polynomial hardness of ring LWE, we still get hardness, but it sets in a little bit later. So not at super logarithmic sizes, but at super linear sizes. Okay. Also here, I want to give you an idea of how we prove this. I'll be a little bit hand-wavy. I just want to communicate the idea. And in fact, since we posted our paper, we've been made aware that there are different ways of proving this. So you can also get this from, for example, computational versions of no-cloning theorems. We do it in a different way. So what we do is we first assume that you have a learner for a class of states that forms or that is pseudo-random. So pseudo-random states are essentially states that are hard to distinguish from truly Ha-random states. And if you were able to learn such a class, then you could also distinguish it from Ha-random, which contradicts the very notion of what a pseudo-random state is. So this distinguisher built from a learner is a standard tool in classical learning theory, and it's relatively straightforward to translate it to quantum. So now the question is, where do you get such a pseudo-random state ensemble from? And here we can rely on prior work that showed that if you can if ring LWE can only be solved in at least T of n time on a quantum computer, there are pseudorandom quantum states that are secure against quantum adversaries that run in roughly the same time, and that and these pseudorandom states can actually be prepared with a gate complexity of n times polylog n. So this is something we take from prior work. Okay, and then the question is, how do you get from the n to the n times polylog n to the logarithmic size that I claimed? You again use the squishing idea. If you assume that this T of n is actually an exponential, then you can start squishing and it's going to work out for you. But the underlying idea is really learning allows you to distinguish a pseudorandom object, which is efficiently preparable, from a truly random object. And therefore, learning is hard if you can implement pseudorandom states in small circuit sizes. Okay, that brings me to the end of the theory part for the states. I want to just give one slide about the numerical experiments we did. Let me warn you that I'm not an expert in numerics, so this is in particular something where some of my co-authors will know better. But the only thing I want to say is that these numerics really help us confirm the theory that we found. So what you're looking at are two plots, where we plot on the x-axis the number of gates in the circuit, and on the y-axis we plot the number of samples that we used. And then you have this contour plot. In the left, so in both cases, the number of qubits is very large. So the number of qubits is in fact 10,000. The point of doing this with such a large number of qubits is to demonstrate that the number of qubits doesn't matter. So as I showed in my bounds, the only thing that matters is the number of gates. So the fact that we can even do all of this for such large numbers of qubits in a classical simulation, I think really hits home or drives home the point that the system size doesn't matter. And then the difference between the left and the right plot is the way in which we generated the states. So what you see on the left are essentially the states that I showed you in this lower bound proof. So where we concentrate all of our gates on the first few qubits. In this case, it was the first 4 qubits. And on the right, we just place the gates at random on some qubits in the circuit, but the number of gates stays the same. Okay, and then what we did is for, okay, I'll leave out some details, but essentially what we did is for different gate sizes and different sample sizes, we ran our learning algorithm and checked what fidelity it achieves. So what you see here in the straight lines, sorry, not straight, in the solid lines, is the average fidelity achieved by our learner. We chose fidelity mostly for convenience. For pure states, fidelity and trace distance are anyways directly related, right? And what you see is that in both cases, the sample size, if you fix a desired target fidelity, the required sample size really does grow roughly linearly with the number of gates. And then the other thing you see is that, so here we plotted also the median fidelity. Turns out that the median fidelity is better than the average fidelity. That's not much of a surprise. In the case of the median fidelity, we're just plotting one single value because actually they don't differ much depending, like if you take 0.9 or 0.99 or 0.999, you get essentially the same curve. This is just the case for our experiments because here we actually used for simplicity a discrete gate set. So you can identify states perfectly, and this, at least we think this is the reason for why you don't see a difference in the median fidelity. Okay, so roughly, I hope this convinces you that the theory also is matched up by some experiments, even though the experiments are relatively basic. Now, I spent a lot of time talking about states, and the reason for that is that now I want to talk about unitaries. And here, in fact, the story is similar in many ways, but with some fun, subtle differences. So first, let me again give you a picture. So Now the idea is, again, that I give you n copies of an object, but now the object that I give you copies of is the circuit itself, so the circuit with g many quantum gates. And giving you access to copies of a circuit essentially means that I allow you to query the circuit n times. So you can pick what input state to feed in, and then you can perform a measurement on the output state. And your task is to learn a circuit description that approximates the true circuit well. So based on what we just did, we saw that the sample complexity of tomography for G-gate states scales linearly in G. So you might hope to see the same behavior for unitary tomography if the unitary is promised to have only G many gates. Unfortunately, the answer to this is no. So this is not actually the case. In fact, there's a relatively easy way to see why an exponential scaling in G is the right thing to do, or the right scaling to expect. The first, so this argument, I'm just going to sketch it for you, is a Grover-based argument. So it's not based on Grover's algorithm, it's based on the optimality of Grover. So let's imagine that we have a bit string of length 2 to the k. And let's say it has Hamming weight 1. So it's a bit string that has 2 to the k entries, but only a single 1 entry, everything else is a 0. And now you could consider a unitary that implements a phase exactly where the 1 is, right? So it flips the phase of the computational basis state that corresponds to the index where the string has 1. Now, if you're trying to learn this unitary to accuracy epsilon in diamond norm, which is a worst case measure, you essentially have to find out where the 1 is among the 2 to the k possible positions where it could be. And by Grover, we know that the best you can do here, sorry, again, not by Grover, by optimality of Grover, we know that the best you can do is essentially 2 to the k half. So you have an exponential scaling in k. Now, the only thing you have to understand is what value of k can you reach with G many gates. And here, you can show that if you want to implement if you want to get 2 to the k length bit strings, it suffices to have linearly in k many gates. And if you combine these facts, you see that essentially by optimality of Grover, you already get an exponential lower bound. So that's a little bit disappointing, right? Because in the state case, it worked, but in the unitary case, somehow the promise doesn't help us, or it doesn't help us much. And if you do this in in a more rigorous form, and you also want to take the dependence on the accuracy into account, you get this theorem. Essentially, what I want to communicate here is really just you have an exponential scaling if you're trying to do this in diamond norm distance. So, and we give an algorithm that achieves it. It's a little bit worse, but okay. So the question is, what went wrong here, right? And okay, you could argue nothing went wrong. It's just the way the mathematics turns out. But what we propose is a slight change of perspective. So essentially, the reason why it didn't work was that we looked at this worst case distance measure, right? We were saying there's a single 1 somewhere, and you have to find it. So this was the task that we looked at. Now, effectively, in the unitary case, this is the same as learning the unitary operator norm up to a global phase. There's some constant factors that I don't remember, but these two are essentially equivalent. So if it's not possible in the worst case, a computer scientist typically asks, is it possible in the average case? So here, we now say you don't want to learn the unitary in operator norm. Rather, you want to learn the unitary in normalized Frobenius norm. So whereas the operator norm looks at the maximum eigenvalue, the normalized Frobenius norm takes a 2-norm average over all eigenvalues. Or in other words, in the example that we had before, if there's a single 1 somewhere, the operator norm will force you to find that 1 on the diagonal. But in normalized Frobenius norm, you don't have to find it, because if it's just a single 1, it will not be make a contribution that you see after the normalization over the exponentially many diagonal entries. So that's the intuition for why this could help. And then if you want, you can rephrase sorry, I'm not sure why my slides are displayed slightly wrong. I hope you can nevertheless read it. So if you rephrase this, you can give it a more operational interpretation as saying that your distance measures the distance in the following process. You pick a state psi at random from the Haar measure, and then you check what's the trace distance between your unitary acting on that state psi and your unitary approximation acting on that state psi. And okay, for convenience, you take a square, and then outside you take a square root. But you can think of this as something like an average case trace distance over Haar random input states. And okay, you can't quite read it, but we denote this by this D average. Okay, and here I've finally got good news. So in this setting, we can recover the result that we had from the state case. So the number of queries to the unitary that you need is at most G over epsilon squared up to log factors with this average case distance measure. And the linear scaling is necessary. And okay, in the epsilon scaling, we don't quite have matching upper and lower bounds. They match up to a polynomial. So the picture that you should have in mind here is that as you increase the circuit complexity, the state learning and the average case unitary learning sample complexity behave in exactly the same way. They just scale linearly until they hit an exponential size, and then they plateau. The worst case unitary learning is much, much worse. It grows exponentially and therefore hits the exponential plateau way earlier. So this is some of what the change from average case to worst case distance measure brought us. Some bits and pieces I wanted to mention is that this procedure essentially is use the unitary to prepare choice states and then run the state procedure on the choice state. We also have a procedure that does not require entangled inputs. It's slightly worse though. It still scales linearly, but it scales worse in epsilon. Now, I think in the interest of time, I'll skip the proof sketch. I'll just say that you reduce it to the state case. And the lower bound case is the same as before. You have to do some squishing, only that you need slightly different arguments for the lower bound. Okay, sorry for skipping over the proof, but let me say one more thing that maybe you can try to follow or that might be interesting for you is I said in the theorem that there is this gap between the 1 over epsilon squared scaling in the upper bound and the 1 over epsilon scaling in the lower bound. In quantum metrology, this difference would be called the difference between the standard limit, that's the 1 over epsilon squared, and the Heisenberg limit, that's the 1 over epsilon. And the question that we haven't been able to answer is whether the correct scaling here is the standard limit scaling or the Heisenberg limited scaling. So can we close this gap? We made only partial progress. So adapting some ideas from prior work by Ha et al. About unitary learning, we can achieve a 1 over epsilon scaling, but for us it comes at the cost of an exponential scaling in the system size. So this is obviously not what you'd want. You'd like to have good system size scaling or no explicit system size scaling and Heisenberg scaling in the accuracy, but we weren't able to achieve this. So one question that we leave open for now is whether this exponential and n scaling in the Heisenberg limited regime is actually real or whether it's just a shortcoming of our proof technique. So you might now be able to see what my next slide will be. I told you about query complexities. So obviously, I'm now going to mention computational complexities. And here the story is really the same as in the state case. So even in average case learning, assuming the same hardness of ring LWE, you get exponential runtime lower bounds. So we have the same variations as for state learning. So you can, for example, also do this for Clifford circuits with super logarithmically many T gates. And the proof is essentially the same, only that you don't need pseudorandom states, you just need pseudorandom functions. And then you distinguish pseudorandom functions from truly random functions by learning the unitary. If you're interested in this proof, or in this computational lower bounds, I'd argue that the unitary case is actually easier than the state case, just because you don't need the pseudorandom state complications. Okay, that's essentially everything I wanted to tell you about unitary learning. Are there any questions about this? Oh,
Hi, Matthias. Can I ask maybe one very basic question?
please.
Yes. So yeah, in the case where you're talking about the learning of the gate unitaries, is it possible to kind of I'm not sure if this question makes complete sense, but is it possible to kind of extend the analysis by, rather than having unitaries, talk about any kind of quantum channel?
Yeah, that question totally makes sense. And so it is an open question that we raised in our work. So it's relatively straightforward to extend our lower bounds. So if I go to the theorem, so the lower bound in red will extend to channels. And I would suspect that in the channel case, you can even get the 1 over epsilon squared. Interestingly, we currently do not know how to translate the upper bound. The annoying parts are, if you try to do this, that on the one hand, we really rely on the fact that fidelity and trace distance are intimately related for pure states. You can make it work for mixed states as well by upper bounding the trace distance in terms of fidelity, but it doesn't work out as nicely. And then parts of our protocol really rely on the fact that states are pure, in the sense that we require some of the operations that appear to be low rank. So if you have higher rank states, you will lose some of the efficiency guarantees of our procedure. And this can actually break it. So if you ask me, my rough conjecture is that if you focus on low rank states, so not necessarily pure, but maybe of some constant rank, I would expect you can do something similar, and okay, the rank will probably play a role. But it isn't obvious. You have to do some, you have to have some ideas on how to vary our procedures. So yeah, I think you're making a very good point. Like, this is one criticism of what we do. We're only doing pure states and unitaries. So essentially, we're assuming noiseless quantum processing, which is not particularly realistic. And incorporating noise, I think, is a natural question that, that unfortunately we had to leave for follow-up work.
Okay, no, thank you for that. Yeah.
Yeah. Further questions about this one? Okay. Then, so as I predicted, and as has always been the case when I gave this talk, I don't have time to cover the quantum no-free lunch theorem and our results for learning physical functions in detail. So I'll postpone it. But what I'll do is I'll give you an idea of what we do here. So the first thing we do is we ask, how much would classical descriptions help you here? So we looked at learning a quantum circuit where the way you access the circuit was you could give it an input state, but it had to be a quantum state. And then you would get out a single copy of the output state. So we are asking, what happens if instead I allow you to essentially do tomography for both input and output states? So you have a classical description of the state that you're putting in. Presumably you also have this in the other scenario, but okay. And then you get a classical description of the state that's coming out. And what you're using for learning are these classical descriptions. So what we show is that if you work in this scenario, then essentially these problems that we had before go away. So you get a much better scaling. And the intuition for this is that, so the underlying question is, why is the sample complexity for unitary learning the same as the sample complexity for state learning in this average case unitary learning scenario? Because intuitively, there should be more to it. But roughly what this suggests is that the challenge is actually a readout problem. So the challenge is you're given an output state from this unitary, and you somehow have to get information out of it. And the complexity of the unitary learning is essentially the complexity of this readout problem. And what we show and what we put in the context of so-called no free lunch theorems in quantum machine learning is that if you're given these classical descriptions, the process learning problem really trivializes. So, and there are some subtleties here depending on what kind of states you can put in. But if you're interested in this kind of thing, I suggest having a look at what we call quantum no free lunch theorem in the paper. And the second aspect that we also talk about in the paper is the idea of learning physical functions. So here we introduce this notion of a physical function that you may or may not agree with. So we say a function is physical if it's a function from real parameters to reals that you can represent as the real parameters being encoded in a quantum state. Then you're running a polynomial-sized circuit. So G, you should imagine here as a polynomial. You get the state out, and you measure it to get an expectation value. So a physical function is a function that you can implement with a quantum experimental setup of this form. And then the question is, can you learn these physical functions, which are just functions with classical input and classical output from data? So what we show is that, or what we ask is essentially, how do these physical functions relate to the class of functions that you can represent with classical neural networks? And what we show is that they face some very similar limitations as classical neural networks do. So in particular, there's like a certain class of nice functions, namely bounded Lipschitz functions, that you would like to be able to represent with either a neural network or a physical function. The problem is if you want to represent all those bounded Lipschitz functions, then the number of parameters in your neural network, as well as the number of gates in this quantum circuit here, will blow up. So there's a curse of dimensionality here, where the number of gates grows exponentially in the dimension of the input. So here on the picture, it's 5, but in machine learning, typically it's not 5, it's much bigger. And this curse of dimension appears in the same way in classical neural nets and quantum physical functions. At least that's our argument. So from this perspective, the expressive power of physical functions is not really bigger than that of neural networks. And consequently, you get learning problems, because if the number of parameters or the number of gates is exponential and the complexity of learning scales with the number of gates, you've lost. So this is the story around physical functions that we developed in the paper. I should say that this is not the end of the story. So there are, in fact, some other papers that have similar ideas around physical functions, and they're actually more positive about their potential. But I wasn't fully convinced by these other papers yet, because while they do show that physical functions can have some advantage over the classical neural nets, it's improving from an exponential to a slightly better exponential. And since I'm worried about exponentials, we took the more pessimistic perspective here in this paper. All right. So now let me conclude. So what did I tell you about, and what are our next questions? So I told you that we proved these tight sample complexity bounds for tomography of bounded complexity pure states. And we have essentially tied query complexity upper and lower bounds for learning unitaries in the average case. So here, the reason why we looked at average case was that the worst case is provably hard. And the reason why I cannot claim tight bounds here is because of this Heisenberg versus standard limit issue that I mentioned before. And then finally, we showed that essentially you get computational hardness for both the state and the unitary case at even slightly super logarithmic sizes, if you're willing to assume that ring LWE really is a very hard problem for quantum computers to solve. So in terms of directions, I think this first direction is what Graham already mentioned. So extending this beyond the case of pure states and unitaries to mixed states and channels is, to the best of my knowledge, still open. And I think there are some interesting challenges in doing this. Another direction is potentially circumventing the computational hardness by inserting additional structure into the circuit. So, for example, we allowed arbitrary circuits of a certain size, but maybe you not only want to restrict the size, but also the depth. And in fact, there's been some recent work. I'm only citing one here. Oh, citation isn't showing up. Okay. There's recent work by Robert Huang and collaborators on learning shallow quantum circuits. So if you're additionally imposing assumptions on the depth, this can really help you get computational efficiency. And then finally, I think a fun question is, for everything that I showed you, we assumed that the circuit structure is variable. So I didn't know in advance where the gates would be placed. I just knew how many gates there would be. So you can ask whether you can improve our bounds in this scenario. And you can think of this a little bit like a sample complexity version of the Brown-Susskind conjecture. So what we show is that as circuit size increases, the learning complexity increases linearly with the circuit size. The Brown-Susskind conjecture is about a random circuit, typically a brickwork circuit, and increasing the size of that circuit and asking what's the actual circuit complexity of the states that you generate. And since this is usually considered in the context of a fixed circuit, I think you should probably fix the circuit structure if you want to have like a learning version of it. This is quite hand-wavy. I'm not an expert on the Brown-Susskind conjecture, so I apologize if I misrepresented it here. And then finally, as I said, in the average case, we have this open question about the Heisenberg scaling that I personally think would be interesting to resolve. Okay, that's it. Thanks a lot for listening. And if you have further questions, please go ahead and ask.
Okay, thank you, Matthias, for that very interesting talk. If anybody has any questions, please just unmute yourself and feel free to ask. While we wait for somebody, maybe I can ask just a very well, it was more kind of a comment of trying to understand. So
yeah,
with the state case, I was trying to understand like the squishing thing that you mentioned.
Let me try to find the slide.
Yeah.
Oh, there must be a faster way of doing this, right? It should be somewhere here. There we go. The pictures or what's helpful?
I think it was maybe a couple of slides before the pictures, if I remember correctly. Yeah, like I could be completely wrong, but my understanding is this kind of squishing is that you're trying to reduce the kind of the set of states you're interested in to those which are you can potentially produce with this number of gates. I don't know if that makes any sense. Is that what this?
You're right. So essentially, we're saying the class of states that we actually consider is all possible n-qubit states that you could prepare with g many 2-qubit gates.
Mm-hmm.
So in particular, this involves circuits, all possible circuits of size g. So now what we're saying is look at a very stupid subclass where we're going to a relatively high depth. So we're going to depth roughly g over log g, which is pretty deep given that you only have g many gates. But I'm saying focus on a very small number of qubits. So you're right that we're kind of focusing in on a subclass of all the possible states that we care about. And we show that for even that subclass, we prove these learning lower bounds. So because they apply to the subclass, they also apply to the larger class. The reason we do this is for like mathematical simplicity, because it's a bit hard to treat the general class. Intuitively, I would expect that even if you don't allow me to do this squishing, there should still be lower bounds. But the fact that for shallow circuits, the scaling is better suggests that my intuition isn't fully correct. So for now, the best I know how to do here is the squishing to get the lower bounds.
Okay, thanks. Is there any other questions from online participants or in person?
I have a question. Okay.
Go ahead.
Hey, Matthias, thanks for the great talk. It's basically a question on your final slide when about the additional structure.
Yes.
conclusions. So I'm just wondering, I mean, I don't know if this is like might be something interesting, or yeah, I'm kind of asking your opinion. So on like adding additional constraints, would it be useful to, instead of just focusing on something like low depth, focus on a structure that's like, you know, goes by a very specific pattern, like all your gates are kind of nearest neighbor connected to each other in a long string, or like these kind of more structural constraints that has large depth, but maybe in the structure there's something that makes it computationally more tractable. Do you feel like that's a also interesting thing you can do?
Yeah, I think that's a good question. So if you ask me to bet, there are some structures that I think won't help you. So for example, if you have a brickwork circuit, so nearest neighbor interactions where you have these layers and then you shift them by one every time, my guess would be that they have the same behavior. And the reason for that guess is the Brown-Susskind conjecture. So for these brickwork circuits, if you randomize them, we somehow know that you expect the circuit complexity to scale linearly, if I understood it correctly. So I believe that this structure probably won't do the trick. But I could definitely imagine that other structures in how you place the gates can help you here. Essentially, we were kind of lacking good candidates, and we didn't look into this more, therefore. But yeah, I think so. Geometric locality alone is not enough, I'm pretty sure. But if you impose further restrictions beyond that, I mean, in particular, we also just we have arbitrary interactions, right? Two qubits, but arbitrarily far apart. So it might be that if you impose some more physical assumptions here, have some underlying structure for the qubit layout or so, maybe you can get something better.
Yeah, I was thinking of something like the tensor network ansatzes,
Yeah.
like a Mira or like the street tensor network. Okay, but they kind of like it's logarithmic, but you know you get to exploit that structure for it's like computationally efficient. So I was just wondering, like other kinds of, you know, those kind of patterns that might be,
Yeah.
how you would include, or which ones you would consider, and how you would include that in like studying the computational hardness. Yeah.
Yeah. So I think from like the tensor network literature, there really is quite a bit where you could hope for efficient learning. I'm not so sure about. I think there are maybe no proven computational hardness results there. There are some results about, so remember, like the computational hardness result, essentially what we used were some results about being able to implement pseudo-random states with these circuits. I think there are some results about implementing pseudo-random states with matrix product states. And essentially the idea is that matrix product states with, I think, at most logarithmic bond dimension are not able to do it, because then you could distinguish them from Haar random by, I think, just estimating the entanglement entropy across cuts. So potentially to get computational inefficiency in the tensor network case, you actually have to go to the regime of large bond dimension where you naturally expect computational inefficiencies to arise. So probably that's a good kind of area for computational efficiency. And I think there's been a paper by Steve Lamire, among others, already in 2013 or 11 or something, about efficient MPS learning. Hopefully this is a paper that I cited on one of my intro slides. So there you're right, like this kind of structure really helps a lot. So maybe from kind of this way of thinking about it, maybe a good way of thinking about structure is not actually just circuit structure, but potentially some other structures.
Yeah.
Yeah, I think I was thinking about this paper by Kramer et al. From 2010. I think they do MPS learning.
Okay, cool. Thank you.
Okay, are there any other questions? Okay, if there's no other questions, then since it's 5 past already, maybe I can just thank us again. And yeah, hopefully we can keep in contact. And yeah, thank you again.